All right, so we're going to talk about section 9.1. We're going to be starting in chapter 9, sequences and series. Some of you may have covered something similar to this in an Algebra 2 or pre-calculus class. So we're going to start out defining what a sequence is, and we'll talk tomorrow also about what a series is. And what our focus is going to be is talking about if sequences and series converge or diverge. And we'll be able to connect the concept of integration to proving this as well. So the first thing we want to look at here is this original definition. A sequence is an infinite list of numbers, and we use this subscript, little s sub 1, little s sub 2, etc., where s sub 1, which is what we call this, is the first term, s sub 2 the second one, etc. So for example, the sequence of squares can be listed as 1, 4, 9, dot, 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 n squared. So each term in the sequence is s sub n equals n squared. They're going to look a lot like functions. I happen to not be a super fan of the little s. Some books use little a. I don't like little s because capital S is going to mean something different, and little s and capital S look the same. On board work, I will try and make it obvious when it's a capital S. I usually underline it to emphasize it's capital S so we can tell the difference. So we realize here, though, since these are terms in a sequence, the input is the position, where in the sequence is that term, and the output is the value of the term. Therefore, the input, the domain, has to only be positive integers, 1, 2, 3, 4, 5, etc. So notice they mention, even though we usually write it with the subscript, sub n, you could think of it as a function, s of n, where that input is the position in the sequence. So let's look at a really simple example to get started for that. So let's just consider if we have the sequence s sub n equals 2n plus 1. Right? So this looks like a linear equation, and you could think of it as a linear sequence. But remember, because it's a sequence, our input has to be positive whole numbers. So in other words, you're thinking of just a list of terms, the first term, the second term, the third term, the fourth term, etc. This right here is your n's, right? That tells you where you are. So to find the value, I plug it in. So s sub 1 is going to be 2 times 1 plus 1, or 3. S sub 2 would be 2 times 2 plus 1, or 5. This one would be 7, 9, etc. So that way it's just a list of terms. The next thing we're going to want to do is talk about how we can represent these terms, so different numerical, algebraic, and graphical viewpoints, and then what we can do with this list of numbers. Talking about if the list is going to be converging, diverging, we're going to add lists together, and all kinds of fun and exciting stuff. So in example 1, we have listing just the first 6 terms in the sequence. This should just be plugging things in. I know you guys can all read, so I'm only going over some key examples, and we'll do some practice on our own. And the second one is working backwards. These problems tend to be a little bit harder. I do assign them for homework because I think it's a nice challenge to try and figure it out. If I give ones like these on a test or a quiz, they should be pretty straightforward. So by working backwards, meaning you have a pattern and you're trying to write an expression or a formula for the pattern. It's a little bit of guess and check. I always start out with the easiest thing and work backwards. So the easiest way is if it's linear, if there's a constant difference. I see here, unfortunately, that's not the case because here the difference is 1, here it's 2. So the next thing you might try and do is squaring, which is what they have here. And here we can see this is the squares. 1 squared, right? Or they have... looks like the power is kind of going back, right? This is like 2 to the 0, 2 to the first, 2 to the second, 2 to the third, right? And some people can find this more quickly than others. This one is the trick, right? This is really 7 over 14. So it looks like in the top they're always 7, and then the pattern is really changing in the bottom, which is linear because I start at 2 and I keep adding 3, right? So the slope would have to be 3 and the first term is 2. What you'll notice with these ones when you're working backwards, so to speak, is that there's frequently more than one answer. As long as your answer gives the same sequence, that's fine with me. The other thing to discuss, 2 more things to discuss, and then we'll look at some more examples, is that there's 2 different ways you can visualize a sequence. So one, we had the algebraic expression. I could also look at it as dots just on a number line, right? Or I can look at it as a 2-dimensional graph where my input is the term in the sequence, and my output is the value. And this is where you can see we can start talking about convergence and divergence. Like in this case, it looks like the terms start all over the place, but they all start coming together at 1. This one, if this is 1, this is 2, this is 3, this is 4, this is 5, this one looks like it's also all going towards 1, bouncing back and forth between positive to negative. So this is a nice visual aid if I want to see what the terms of the sequence are doing. As I move down the list of numbers, what happens to them? So, for example, let's go ahead and try writing out in a plot. Let's look at, so let's here consider, if I can actually get my thing to move down. Maybe not.